This video is about deriving a conditional statement. Suppose I'm trying to convince you of this claim down here, that if you graduate college, then you earn more money. And I try to convince you of this by presenting you with an argument that has two premises, which say, first, if you graduate college, then you will get a better job. If you get a better job, then you earn more money. Therefore, if you graduate college, you earn more money. Well, what if you were not so fully convinced that this argument was a good argument? You could check it for validity using a truth tree or a truth table, and you would begin by symbolizing it. So let's first symbolize it using the obvious sentence letters. If you graduate college, then you get a better job. If you get a better job, then you earn more money. Therefore, if you graduate college, then you earn more money. And that indeed would be a valid that comes out as valid if you do the truth tree for it, for example. But what if you wanted me to show you how to reason your way from the premises to the conclusion, instead of simply showing that there is no way to make both premises true and the conclusion false? Well, I might do that by reasoning my way to the conclusion in the following way. And what I'm going to do now is write out a sort of rough sketch of a derivation. I might say, well, look, first, let's just assume that my premises are true. Let's assume that if you graduate college, if G, then B, you get a better job. And let's also assume that if B, if you get a better job, then you earn money. If you grant me those premises, which I agree right now, they're just assumptions, right? But if you grant me those premises, I can show you that it follows that if you graduate college, then you earn more money. And the way I do it is like this. I say, okay, now that you've granted me those two premises, let's also assume that you graduate college. This is a new assumption, because I'm trying to show you that if you assume that you graduate college, then you earn more money. And now I can say, well, look, since we had already assumed that if G, then B, now that I have assumed G, I can infer B. And that comes from lines 1 and 3. And then once I've inferred B, I can infer M from lines 2 and 4. And so therefore, what I can conclude is that if I assume my premises and I also assume the antecedent of the conditional, I can derive the consequent of the conditional. So in other words, here's another way to say that. If I assume my premises, then what I've shown is that if G is true, then M has to be true. So in other words, what I've shown is if G, then M. And this last line here is what motivates our version of the conditional introduction rule. So let me show you how to write out the conditional introduction rule, and then we're going to rewrite this derivation using all of our proper notation and all of our proper scope lines. So the conditional introduction rule says if somewhere along a derivation, I can first assume script P for the purposes of using conditional introduction, and then on the basis of that assumption, derive Q, then what I can conclude or what I can infer is that if P, then Q. And if that's line N and this is line M here, then my notation is that that comes from N through M. And I use a dash here to indicate that I'm using all of these lines in between N and M. And then I'm using the conditional introduction rule. Okay, so you're allowed to introduce a new assumption. Whenever you do, you must state that it is an assumption, and you must state the rule that you plan to use that assumption with. In this case, our assumption is going to be used for conditional introduction. Once I've derived what the rule requires, which in this case is the consequent of the conditional, I stop this scope line, and we call that discharging the assumption, and then we can write the conditional. So now let's rewrite our derivation using all of our textbook perfect notation. So we started with line 1 was if G, then B. And line 2 was if B, then M. And these are what we now are going to start calling our primary assumptions. So they just get labeled with A's. Those are what we are given as premises in an argument. Then what we did was make a new assumption. So this is the first time we are using what we call a secondary assumption, or sometimes they're called auxiliary assumptions. And we're assuming G for the purposes of conditional introduction. And notice how I vocalized that. I very deliberately said assuming for the purposes of, because I always have to have a purpose or a reason for making an assumption. And my assumption is for the purpose of using a conditional introduction. Now on line 4, I can infer B from lines 1 and 3 by conditional elimination. Notice, as always, my conditional elimination rule has to have 2 line numbers because it's a 2-premise inference rule. And then on line 5, I can write down M, and that came from lines 2 and 4 by conditional elimination. And now what I do is I stop drawing the vertical line that was right beside G, and I write the conditional beside the leftmost scope line here. And keeping these scope lines starting and stopping in the right place is really, really important. So I now write G arrow M, and the notation is 3-5, because to introduce this conditional, I had to use all of this reasoning, the reasoning that goes from lines 3 through line 5. That's why I write 3-5, conditional introduction. And that is now a complete and correct derivation of the conditional G arrow M from the two premises G arrow B and B arrow M. So let's focus on just 4 important things to notice about derivations. The first thing to notice, I already mentioned before, whenever we make a secondary assumption, we must be doing it for the purpose of using some rule. And you'll notice that when you stop the scope line, the line directly after you scope the scope line, the rule matches. I assume this for the purposes of conditional introduction. And then on line 5, I discharge the assumption using the rule that I started with. So these will always match. Okay, these are basically matching what's going on over here. Okay, so now that's the first observation to make about this. The second observation to make about this is that once we discharge an assumption, we no longer can use anything that is directly to the right of that scope line. So for instance, at line 6, I could continue my derivation if I was setting out to derive something else. So for example, I could, on line 7, write down G arrow M and B arrow M and say that that line came from 2 and 6 by and introduction. That's a perfectly legitimate step to take if I wanted to derive this longer sentence. However, what I cannot do, I cannot, for example, on line 7, write down M from 3 and 6 by arrow elimination because 3 is beside this secondary scope line that I've already discharged at line 6. So once I discharge an assumption, once I stop this scope line, it's as if everything inside here is now out of reach. I can no longer use anything inside this red box further down in my derivation. And that's a very important role that these scope lines play because they guarantee that even though we are using additional assumptions, we are not misusing additional assumptions because we're being very careful about tracking what we derive from those assumptions at every step of the way. Okay, so another way to remember this is that once I've started a new secondary scope line, right? So if I'm, for example, still working on this derivation and I am here, say here at line 5, if I'm inside a secondary scope line, I can use anything that is directly above and to the left. Okay, so at line 5, I could use lines 4, line 3, line 2, or line 1. But once I discharge the assumption at line 5 and stop this scope line, at line 6, the only lines that I have access to are lines 1 and 2 up here. I can no longer use lines 3, 4, or 5. And so that's a very, very important thing to remember. Please try to go through this a couple of times and convince yourself that you understand how scope lines work.